Welcome back, everyone. For the second part of Chapter 1, we're going to be talking about Earth-Sun relations. So what we want to know is where the sun is shining, for how long and how intensely, and what are the effects of this. So the Earth's rotation, the Earth rotates once in 24 hours. It spins on its axis, which goes from the North Pole to the South Pole, and that's why those are the poles. And it takes 24 hours to do so, and that's one of our days. It spins from west to east, which is why our sun sets in the west and rises in the east. And again, it spins around this imaginary pin through these poles. It orbits around the sun, and this is, so again, this is not a rotation, this is a revolution, around the sun on this plane of the ecliptic. So the plane that it operates on around the sun is the plane of the ecliptic. It takes 1 year to complete one revolution around the sun, right? And this is how our years are divided, right? We go around the sun once in 1 year. It takes 365.25 days. That 0.25 is why every 4 years we have a leap year. We have to get that extra day in somehow. And it has an elliptical shape. It's not a perfect rotation. A part of the year, it's closer to the sun than it is at another part of the year. So the perihelion is when it's closest to the sun, and which is in January. The aphelion is when it's farthest from the sun, and that is when it is in July. This is not the reason for the seasons. We're going to talk about the reason for the seasons moving forward, but this is not why. But the important thing to remember is it takes 1 year for our planet to revolve around the sun. It does so in an elliptical shape, and it's not always the same distance from the sun. In January, we are closer to the sun than we are in July, which might be a little counterintuitive for us being in the northern hemisphere, but in the southern hemisphere, it's not going to be. When we look at what part of the Earth is illuminated by the light from the sun at any given time, exactly half of the Earth is illuminated by sunlight. This is called the circle of illumination, that boundary between the light half and the dark half. And we couldn't really see this very clearly. We knew it, but we couldn't really see it before we sent people to space in order to take pictures of it and sent satellites up. We knew that it was half, but it's really kind of a very stark image. Our Earth is rotating on a tilted axis. The axis is tilted 23.5 degrees off the plane of the ecliptic. And so I'm just going to back up for 1 second. So when we look at this Earth rotating around the sun here, what we can see is that it's tilted a little bit. Go back. There we go. The northern or southern hemisphere is angled toward or away from the sun during certain times of the year. This results in an uneven distribution of sunlight, and this is what causes the seasons, which I know I just went through that very fast, but if we slow down for a second, you can understand what I mean. And so basically, during our summer in the northern hemisphere is receiving more light than the southern hemisphere is. During their summer, which happens when we have our winter, they are getting more sunlight. And we'll look at some examples of this. So just some important terms and concepts to remember going forward. The solar angle is the angle of the sun's rays at the surface. The declination is the latitude of the sun's direct rays, 90-degree solar angle. And so basically, the solar angle, if you look in the sky and see where the sun is at any given point, you can kind of raise your arm up a little bit and make an angle at that. That angle is a solar angle. The declination is the latitude where the sun is directly overhead. It's constantly but slowly changing, and it's always between the tropics, that 23.5 degrees north and south that we looked at previously. And we'll look at some more examples of this or some more illustrations of it. But again, the declination is the latitude of when the sun's rays are 90 degrees. And so this is why this is the warmest place, the tropics on our planet. The subsolar point is where the sun's rays are striking right now. The solar noon angle is the angle of the noon sun above the horizon at a given latitude on a given day, up to 90 degrees. During winter, our solar noon angle does not get very high, right? So again, if you walked outside at noon in San Diego, looked to see where the sun was, looked at that angle of how high it was in the sky, that's our solar noon angle. It changes throughout the year in relation to the declination. Farther from the declination, the lower the solar angle. So the farther you are away from the tropics, the less high that sun is going to rise in the sky. Some more important terms and concepts. The higher the solar angle means the more intense radiation. This means as you get towards 90 degrees, you are getting more sun, which is pretty intuitive to us, right? If we think about going outside on a summer day, we don't think of needing as sunscreen as much, although we should, in the morning and at the end of the day, right? It's during that middle part of the day when the sun is highest in the sky. That's when we're getting the most intense radiation. It's generally higher at lower latitudes. Again, those lower latitudes, those tropics and near the equator are getting more intense radiation. It's higher in the summer and lower in the winter, which is very intuitive, right? We're not getting as much radiation in the winter. In San Diego, we do have seasons. We do have a summer and the winter, but these are not as drastic as they are when you get farther away from the equator. Higher latitudes have more seasonal variation. So I grew up in Connecticut. In New England, we're at a higher latitude, and we definitely have some more significant seasonal variation there. In the summer, it can get well into the 90s. In the winter, we can have blizzards. And so, if we look at this, is actually a picture looking at kind of an equinox here, right? You got half of the Earth illuminated. The subsolar point, the 90-degree angle, that's happening at the equator. That's where it's getting the most sun. In the northern hemisphere, it's at 40 degrees latitude. You get a 50-degree solar angle. Both poles are getting some sunlight there. But this leads to a variation in day length. So if you've ever traveled towards the poles to Alaska or to Antarctica, right, the higher the latitude, the more variation in day length you're going to get. So the equator is going to get 12 hours every day of the year. Every day of the year, they're going to get 12 hours of sunlight, 12 hours of darkness. In the Arctic and the Antarctic, and we're talking about those circles above 60 degrees north and south, respectively, it's going to limit the amount of light and dark that they get. So you're going to get longer days and more exposure to sun, right? So this is a midnight baseball game in Fairbanks, Alaska, right? The sun barely sets in the summer in Alaska. As opposed to, this is noon in Reykjavik, Iceland, which is at a very high latitude in the winter, right? This is as bright as it is getting in Iceland in the winter. It's pretty cold and it's pretty dark, right? It's not going to get much brighter than this. This looks closer to our sunset, but this is actually their noon. So the summer solstice, we're going to talk about the solstice and the equinoxes. And all of these examples are referring to the northern hemisphere, so we want to remember that. During the summer solstice, the declination, or that place where the sun is getting its 90-degree angle that the sun's rays, is going to be at the Tropic of Cancer. It is the longest day of the year in the northern hemisphere. After June 22nd, which we'll be coming up on in just a couple weeks, our days will start to get shorter. So our days are going to get longer and longer until that point, and then after that, they're going to get shorter in the northern hemisphere. The fall equinox, which happens on September 21st, those sun rays are striking right at the equator, and everywhere on the planet is getting exactly 12 hours of daylight everywhere. The days are still going to get shorter in the northern hemisphere. For the winter solstice, this is the shortest day of the year in the northern hemisphere. And you can see there, look at the northern hemisphere. The pole is not really getting any type of light at all. It's going to be pretty dark there year-round. When I grew up in Connecticut, which is again more north, it got dark at about 4:30 in the afternoon by the time we hit the winter solstice. So pretty dark. That declination is going to be at the Tropic of Capricorn at 23.5 degrees south. And then the spring equinox, just like the fall equinox, everybody is getting 12 hours of daylight everywhere. The days are still getting longer. So it's leading back towards that summer solstice. And again, these are northern hemisphere examples. Seasons are reversed on the other side of the equator. So this is Christmas in Australia, still December 25th, but Australia experiences their summer when we are having our winter. So in summary, two variables cause the seasons. One is that shifting solar angle. During the summer, sun is higher in the sky, sunlight is more direct and more intense. During winter, the sun is lower in the sky, sunlight is less direct and less intense. And that tilt also affects the day length. In the summer, we have longer days. Our days right now in June are pretty long. We get more exposure to the sunlight. In winter, we have shorter days. We get less exposure to sunlight, right? The less time the sun shines on us during the day, the less hot we can get. We can't absorb as much heat. Areas near the equator have little seasonal variation due to both of those variables, right? The equator is has a very high solar angle and is getting a lot of sunlight all year long. So it's going to be hot there all year long. Areas farthest from the equator have more seasonal variation of both variables, right? So there is a ton of seasonal variation in the Arctic. It is always cold, but you have periods of time where it gets hardly any sunlight and periods of time where it gets almost 24 hours a day of sunlight. But the angle is pretty low, so it's not getting a bunch of intense radiation. But the ice sheets up there do retract a lot during the summer. So that's going to be the end of chapter 1. Next, you're going to proceed on to the lecture for chapter 2.